So I would like to briefly introduce today's Tech Talk topic. So we are back after a long break, and so it's a minimal viable data space with Eclipse Dataspace Components and Intel Software Guard extensions. And today we have Markus Leberecht from Intel and Sergiu Stejar from IONOS to present that. And so, as you know, our Tech Talk is being powered by several projects. And so, as every second counts after now, so I would like to kindly invite Markus and Sergiu to the stage. So thank you very much.
Yes, thank you very much, Anil. And apologies also from our side for the delay. And by the way, someone is waiting still in the lobby. Okay. I will share my screen directly and then we'll get going. So get a second. Okay, and I can share, that's good. Here we go. Okay, so a minimal viable data space, that's what Anil already told us. My name is Markus Leberecht. I work for Intel as a solution architect for infrastructure and infrastructure security in Germany, Munich. With me is Sergiu. I'll let Sergiu introduce himself when we switch to him. He's a software architect at IONOS Cloud. We did this jointly as a larger proof of concept within a context that I'm going to explain further. So this is the agenda. We're going to introduce you to what confidential computing is. I assume that quite a number of you will know it already, but just to level set, and I will also give you a bit of an introduction to Intel Software Guard extensions, or SGX, which I'll follow up with a motivation for exactly this project, which is basically coming out of the GaiaX context, in this case, the HealthX Data Loft data space implementation, for which IONOS is a main project partner and we are an associated partner. Talk a little bit about a software environment that we used called Gramine that helps you do things that we did, like lifting and shifting existing applications into a trusted execution environment. And then we'll switch over to Sergiu, who will take over both his minimal viable data space developer journey. There's a couple of lessons learned in there, and we'll show you just by showing you some screenshots about how this looked like. And there's also a video that we can share later on, an unlisted YouTube video that you can look at where this is being actually exercised through by Sergiu. And that'll be it for today. So let's get it started by talking about why confidential computing is needed, or what it is actually represents. If you look at the life cycle of data and data protection, then you know pretty well that there exist established ways of keeping data confidential when at rest and when in transit, both through encryption methods, which at a time when compute platforms were largely not shared, was also sufficient enough, because you would have basically a trusted machine that only belonged to you, and that only was governed by yourself when the data had to be basically unencrypted or decrypted before being processed on, and then when being sent out again, it would have to be encrypted or stored, also would have to be encrypted. Now, with shared platforms that we use today in the cloud, and also in cloud-like or virtualized or containerized environments in private enterprises, there is also the need to protect data in use. Because frankly, can you always be sure that you can trust your hypervisor or the hypervisor admin? Maybe not. And so confidential computing aims to fill this gap by applying the same method of encryption during this stage, basically during processing, of code and data when that is being used. So this data in use protection is confidential computing, and it is typically implemented by processor manufacturers in a very particular way that I'll quickly go through just in principle. Every manufacturer certainly does it in a slightly different way, but essentially confidential computing refers to creating a so-called trusted execution environment. That is a region of memory which holds code and data in a von Neumann architecture that is basically the program, and isolates that by usual methods that you know, like memory protection, etc., from external access, but it also adds a layer of live encryption on top of this. What that means is basically the memory controller has an inline encryption engine that will encrypt every data item, basically every cache line that is written out to main memory, and decrypts data that's coming in from main memory. Per region, it owns individual keys, and so makes various different trusted execution environments, of which there can exist multiple in these platforms, independent from each other. The keys themselves, they are kept inside the processor. They are never shared. They're in parts also randomly generated. You keep them basically outside of the reach of any system software, any untrusted software, any cloud stack, any cloud admin. And by that, also create a nice separation of duties between the tenant on a shared platform versus the operator. So this encryption establishes the control for confidentiality at runtime. It's a very opaque environment, so you may not know what's inside it. But in order to actually do know that what you expect is also inside it without being able to look into it, without being able to read clear text from that region, there's typically verification mechanisms, remote and local attestation mechanisms that these platforms feature, which use cryptographic methods like hashes, for example, to measure the content of that trusted execution environment. Often enough, also, that attestation quote, that attestation evidence includes non-falsifiable evidence from the platform and its state of configuration as well, so that you're sure the firmware of the platform, for example, is in a correct state for this whole affair to function. So that's how confidential computing on a 10,000 foot level works. What can you do with it? Quite a number of things, actually. I already said that it enables a very strict separation of duties and should, when everything is set up correctly, prevent any hypervisor, any admin of a hypervisor, any underlying software stack to access data, even if you're in the cloud that is being operated by someone you necessarily don't always need to trust. Yeah, so this means going to the cloud, even with regulated data, may be possible. It may be possible to establish multi-party computing scenarios where everyone contributes data without sharing them directly with each other. They just share that into a trusted execution environment, and by that get the possibility to compute jointly on a result that everyone benefits from, but no one sees each other's source data. Yeah, and by that, both you get the possibility to harden, let's say, for example, AI models, IP that you have in forms of code and data, or it helps you to stay compliant and to a degree keep data sovereignty strongly under control when you're moving to shared platforms. Yeah, Intel's been on the market with confidential computing for quite some time now, and we have multiple technologies in our portfolio that we're using. And the best way how they are working is explained in such a diagram where you basically showcase what we call a trust boundary. Trust boundary is when you're looking at the trustability of a platform from the perspective of data that needs to stay confidential. When you have a basically a usual off-the-shelf platform without any special protections, and you have confidential data, and you have a stack on which this confidential data sits, then you basically everything that is included here in this trust boundary needs to be controlled, trusted, and is a potential source of danger if not trustable. Yeah, that means if you don't have it under control, you have to be wary of any impact on the security of your confidential data that this might have. There's two technologies that we've brought to market. SGX, Software Guard Extensions, is the older one, and TDX, Trust Domain Extension, is the newer one. They basically differ in the artifact that we're using to establish a trusted execution environment. I'll quickly talk about this because we will not focus on TDX in this talk any further. Trust Domain Extensions uses a virtual machine as a trusted execution environment. As you see here, when you have a virtual machine, then you can basically leave Cloud Stack and admins, the cloud infrastructure's configuration and its basic software stack out of the picture. You don't need to necessarily trust it any much stronger than you would normally do. It's outside of your trust boundary, and therefore it is not able to look into what is inside this confidential VM. The only thing that's usually under your control is your own enterprise organizations, administrators, the deployments you do inside such a VM as the OS and the applications beyond the confidential data. We are focusing, however, today on software guard extensions. And software guard extensions, as you see here, is a technology that's been on the market since roughly 2018, since roughly 2020, I should say, 21. I can't really recall it anymore. It's part of our mainstream server lineup, meaning the high volume dual socket service that you find in cloud infrastructure implementation. And SGX implements a trusted execution environment that is very thin in its trust boundary across around the confidential data. It basically uses a single process to be put into such a trusted execution environment. We call it a secure enclave, and that's what this enclave here stands for. And it's basically the data plus the methods that you want to apply securely on that data. So you can think of that as a secure object in a secure enclave. Even parts of the apps don't necessarily have to be fully trusted. What you have here is basically a very naked environment with a very small attack surface, so making it extremely controllable. On the other hand, that makes it also a little bit more cumbersome to move existing applications, as you see here. They seem to be broken up into SGX, but there are tricks. Yeah. So this is the element we're using today, and we're showcasing today for our proof of concept. Motivated was this whole project that Intel and IONOS embarked upon by our joint participation in the partnership within the HealthX Data Loft healthcare data space, one of the GaiaX Lighthouse projects, where among various iterations of this project, there was one, at least a long-term one, that's still somewhat in focus, where the Eclipse Dataspace connector from the EDC project was considered as the mainstream connection into the HealthX data space that involves here on one side institutions in the healthcare market, a citizen with a data wallet app, and various other parts that usually belong to a data space, such as trust services, catalogs, and with the intent of giving patients, citizens, the ability to be the master of their own data sharing within concepts such as the upcoming European healthcare data space. Now, with healthcare data, the protections need to be quite high, and having SGX proven a proven technology in the healthcare market by its application in the electronic patient record implementation, as well as the e-patient as e-prescription, meaning elektronisches Rezept. In Germany, this was chosen as a demonstrator in our case to deploy EDC inside such a trusted execution environment. So I did say it is a little bit cumbersome to implement existing applications that typically run on a full operating system in a secure enclave with SGX. There are tricks, however, to do that a little bit more easily, and one of those is the open source project Gramine. Gramine is a library operating system, as it's written here. Gramine is sponsored heavily by Intel, but it's an ongoing community development as well. And Gramine basically replaces the typical Linux application binary interface, which is mostly made up of libc calls, system calls, with a library operating system that would sit nicely in an SGX enclave. This library operating system will proxy any service that the application needs from the host operating system, and will transform it securely into a service that can be executed inside the secure enclave. You can find it open source. There's packages for the established Linux distributions that you can easily install. And among the tools that come with Gramine is a particular tool that's called Gramine Shielded Containers, which is basically just a Python script that uses the tools coming with Gramine to convert an existing applications into a Docker container, or an existing Docker container into a Docker container that can run inside an SGX environment. We have used that, as I said, this is a bit of a proxying effort here to just highlight how this looks like. If you have a usual Linux host operating system where you have an application running, Gramine will take that application, that is the green part here, and will bind it with the Gramine library operating system, replacing the Linux API, and place Gramine and a trusted platform abstraction layer inside the SGX domain, SGX secure enclave. And the controlled gates here through the walls of basically the enclave will be tunneled by an untrusted and trusted PAL partnership from Gramine to then execute certain host OS services in the host operating system on behalf of the secure enclave, and then deliver the results back. This is, in some cases, it'll take some performance because you're crossing the boundaries, but typically, if you can, if Gramine can stay within the enclave with the operating system services, it will do so and not waste performance in crossing the context boundary here. And that's actually already what I wanted to present, and I've tried to speed up a little bit so as to give Sergiu most of his time on the MVDS developer journey when we actually applied this. Sergiu, I'll hand over to you, and I will actually flip the screen for you if you give me a hint.
Thank you, Markus. Let me try it out. Oh, if you flip the screen, then it's even better. So, hi, I'm Sergiu Stejar. I'm working for IONOS in Bucharest, in the Bucharest office as a software architect. And mainly I'm supporting the domains, DNS, SSL team with architecture, security, certification, audits, and cloud stuff. And sometimes I get involved in projects like this, which are really cool. So it has been a great collaboration with Markus and Anita, and thank you for all your support during this and other similar projects. So today I'm going to speak about the journey of integrating minimal viable demonstrator from Eclipse Dataspace Connector with SGX, essentially making it run on SGX. So if we go to the next slide, please. This is briefly the diagram of what the minimal viable demonstrator consists of. On the top row, we have dashboards. There are browsers that run stuff that comes from components hosted in Docker containers. And these components interact with the Eclipse connectors. They do the heavy lifting of moving data. So we have three companies, the example of three companies with their dashboards, three connectors, of which two of them we've made run on SGX. These connectors move data from a storage that's also accessed via storage browser, which we'll see in the examples. So data is created for one company, it's made available to the other company, and then is securely transferred in between the connectors. That's the workflow. There are some collateral components to set up the whole thing with data, some CLI tools, distributed identity server so that connectors trust each other, and the registration service so the connectors know about each other. So this is a brief overview. Now, next slide, please. And now, when we started with the Eclipse Dataspace Connector, we had a repo that's available, and we needed to get the whole set of components running. The challenge was that the demonstrator was in a different repository than the core components, and we have the data browser also separate. So we needed to find matching versions that will actually talk to each other in a nice way. And the challenge was that there are no branches or tags, but luckily we found some meaningful commit names. And based on the time of commits, we identified some milestones, and then we well, got it running. Next slide, please. So as an example, the time we've started working on this, the EDC connector was at milestone 8 of version 001. No corresponding minimal viable demonstrator, but there was one at milestone 7, and no data dashboard branches. But luckily, there are only 5 commits in between a certain time frame where we thought things should be. So we found a matching data dashboard commit through trial and error, and finally, Eclipse Dataspace Connector minimal viable demonstrator was running. Next slide, please. Now moving on to preparing it for SGX. The demonstrator comes with a Docker Compose file, which very nicely starts up all components, connects them together, and does everything from building the code to putting the stuff in Docker and making it available. That was not exactly what we needed, because we wanted to be able to invoke images that were pre-built with the SGX support from Gramine shielded container. So the first change was to modify the Docker Compose file so it simply invokes the images that we pre-built. Next slide, please. Now, in terms of building, we had some challenges with running on SGX because SGX is a secure environment, and various features that the components of EDC were using were not available. The challenge was that the code was hiding the exceptions, probably on the assumption that were not really necessary for whoever is running it, and probably that was a fair scenario in the non-SGX case, but in our case, we wanted to see the nitty-gritty details of what happened there. So we wanted to expose the really underlying error, not the exceptions that were nicely made available. So the first attempt was to create a new release of Eclipse Dataspace Connector, pushed it into a local M2 repo, build MVD, switch from fat jars to slim jars, and had some dependency hell to deal with, and eventually gave up this path. Probably would have worked, but the pressure of time, eventually we found a different way to approach it, attach the debugger to the Java process, and then just step through the running code and found the exact thrown exceptions. So that was the first victory in this getting this running. Next slide, please. Now, to run it, as Markus mentioned, we needed to use Gramine shielded containers to wrap the existing Eclipse Dataspace Connector minimal viable demonstrator images into GSC images to essentially Graminize the base images. And this happens in a few steps. The first step is to use GSC to build a base image. For that, we use a manifest file about which I'll come back later with details. So this manifest file tells GSC how to set up the security, mainly the security and the general setup of running in SGX mode for the image that is being wrapped. Now, this base image then needs to be signed, and for that, we have somewhere at the middle of the slide the cleanup of the keys and the regeneration of the enclave key that is stored locally. And this enclave key is used for building a signed image that is then accepted when running it. The final step was to run info image on it to see if everything checks out and is all ready for putting the image into a Docker compose file and see what happens. So that was the next step. Next slide, please. Now we're back to the manifest file. This manifest tells Gramine and the Gramine shielded containers how to configure essentially SGX when it runs. So the first section is about the enclave size. Iteratively, we found a size that's not too large and not too small and contains everything. We adjusted the number of threads. Then we got into more convoluted stuff. Google was our friend. So cryptic errors were solved by just Googling them and finding that other people ran into similar issues. So non-relocatable binaries need to be allowed and supported. Then Gramine needs to know which files are allowed outside that are files that are pushed into the image. So for the timing, we just allowed all configuration files which we knew are safe. So Gramine didn't complain about them. Next slide, please. Also, running a temporary mount is needed, so that was specified. And for the purpose of testing configuration, we allowed unsecure host environments, essentially environment variables that need to be passed to the minimal viable demonstrator. These can be changed with specific specified its host environment variables, but for the sake of the experiment, we just let it like that because we know that is just more of a simple change to do if when we go in production. Also, event FD system calls made by Java had to be allowed, and that was also through trial and error and so search. This is a field of more research when needed, but eventually that allowed us to start up the demonstrator. Next slide, please. When building the image, there are challenges related to Gramine shielded containers as well. Essentially, there are a bunch of Python scripts that do all the heavy work of packaging the image, of building the Docker files based on the platform that's run, with it's Debian or it's Ubuntu, putting all the variables and all the GSE stuff. And one challenge here was about the libcrypto library. So eventually modify the code of the Python script to just find it and move forward. This can be a candidate for a patch, or well, maybe newer versions already have it. Also, challenges with networking. The demonstrator builds its own network, and for that, we had some challenges with GSE, and eventually we created a resolve.conf file mapping IPs that we specifically allocated for each component, matching them with host names, and push those into that conf file into each container. Kind of a hack, but also moved us ahead. Also, when building the containers, GSE needed external dependencies, so we hacked the network mode in host mode, so those external dependency can be pulled in. A lot of corners were cut to get things running. Again, a lot of potential for improvement. Well, the point was to prove that it works, and it worked. Next slide, please. Also, Java complained about things when running. Force the IP4 stack, configure the meta space, compress class pointers, and for whatever reason, we had to say the operating system is Windows. And that made Java happy running in SGX. Finally, all this stuff was running on a machine that was provided by my colleagues from IONOS Cloud in a certain data center, and well, just a server that was configured for SGX. We had VMs running there. That's where we're running, no UI. So since we wanted to use the browser and the data browser to manipulate data, we needed to build tunnels. So yeah, we built a bunch of tunnels between the local machine and the machine where the experiment was happening. So that's how we got to seeing the demonstrator running. Next slide, please. And this is now we'll see a bunch of screenshots from our recording that we've done when running the demonstrator. The environment we had was quite volatile, being an experimental. So, well, that made our scripting much better because we had to refresh it every couple of weeks. So there was a benefit for that, but just to be safe, we have a proof that it works. We record setup. So what we see here is the startup of the Docker containers. It's one of the containers that's running in SGX mode, and highlighted it says Gramine. This is it's a header that proves that now we're running in SGX mode for that particular container. Next slide, please. Again, a bunch of outputs with the initialization of the data, and This proves that all components are running. It's a list of the containers, and we see that some of them show stuff that can be related to SGX and Gramine. Next slide, please. Yeah, that's. Now we get to the interesting part. To move data from one company to the other, we need to seed that data. So we followed the guideline for the minimal viable demonstrator, and we created some files, which using the Microsoft Azure Storage Explorer, we uploaded to the Azure storage running locally. So we selected a file. Here you see exactly the step where the file is selected, so that is uploaded, and then it shows up in the window that's in the right lower corner. And that's for the first company. Next slide, please. Here is where we see the browser of one company. The UI shows multiple stages of setting up. So we see on the left side of the browser getting started, and then there's a section to create a contract in between the companies. Yes, please stay on that one. So what happens is the user goes there and then can select the other company as a destination for the data, and through the registration service, it's able to see that company, validate its part of the environment using the distributed identity using the ID, and then once that happens, that talk happens, a contract is established with the other company. So this is that step. And then the next step is that, next slide, please. Within that contract is to send a file. So after the contract is signed for negotiation, the file is uploaded, and then we see a status. It's a matter of a couple of seconds where the file is securely transferred to the other company. So we see this this nice pop-up that the file is done, is there. Next slide, please. So here, before handing it over to Markus, I say in terms of challenges, yeah, running it in SGX was a challenging stuff. We've done that for a few other projects, but I think the biggest challenge here was to get the base MVD running because of the lack of versions. That took some iterative guesswork before having it done, and then everything else followed as a natural consequence of each error that we've run into. So with that, thank you for listening, and I'm handing it over back to Markus.
Thank you, Sergiu. Yeah, so as Sergiu pointed out, it was ultimately a successful exercise. What he didn't mention, I think, is that we also demonstrated, and that's what you will see in the video, that the interoperability with a protected connector and a non-protected connector is actually the same as between protected connectors. So that's why this triple setup with 2 protected and 1 non-protected connector were chosen in this case. So yeah, continental computing was shown to be fit for this purpose. We did go through some hoops to get it running. Now it's a simple way of just placing the complete connector in a trusted execution environment. There are obviously other variants possible how you could use confidential computing in this context that are much more elaborate. But in this simple way, this demonstrates a hardening around the business logic of any connector that you could have. We used SGX mainly because that was at that point when we started, it was available. Today, you should probably take also slightly other variants like TDX into account. But with the requirements coming from HealthX and also parallel the work that Intel and others are doing in Gaia-X on infrastructure that supports confidential computing, we actually were able here to provide you a playground that worked within this in these constraints around data spaces, Gaia-X, confidential computing all together. So I'm happy that this works. As I said, we will probably share along with the slides, and we forgot to put this in here, the link to the video, so you can watch the actual demo afterwards if you like to. And we luckily have some minutes, and Anil, if that's the idea, we can have a little bit of an open Q&A on this as well.
Thank you very much, Markus. Thank you very much, Sergiu. That was really first. Thank you for sharing your know-how in the IDSA GitHub as well, and then having this comprehensive overview of, over the matter. I think that was an excellent and very comprehensive one. So with this, I would like to invite everyone to use the Q&A, or I think it will be more user-friendly to allow the mic for everyone. So if you have a question, please raise your hand, and then you can unmute yourself. And until then, I may have a question, if I may. Sorry for getting in the first line. So about the negotiating and transferring data slide. You know, we also have the same order in this dataspace protocol. So that is there such a mapping effort? Like, how does that relate to the dataspace protocols, like the catalog protocol, then negotiation, contract negotiation, and data transfer? Is there like any similarity or mapping that you can see so far, or is it?
Well, not specifically sure about the exact ones that you mentioned, but what I would say is one aspect that we didn't focus on in here that's a little bit elaborated on in the IDSA GitHub, where this scenario is being explained, is the aspect of attestation. So basically making sure that what actually is inside the secure enclave is actually your connector and nothing else. Yeah, and that attestation protocol can be mapped to some of the protocols that you are using. It can also be mapped like Gramine, how Gramine offers it within a TLS connection setup. So through sharing the keys and the key exchange setup for TLS, there's a version called Remote Attestation TLS, RATLS, that you can use to kind of under the hood integrate attestation in it before you are trusting another side of this. So there are various possibilities, I'd say. Also, the industry movement towards generalized and standardized attestation protocols is still ongoing. I would say it's a place to watch, yeah, and potential for combining several efforts here.
Thank you very much. Thanks. Looking forward to it. We have a question from Michael Vasiliadis. Please go ahead.
Hello, this is Michael. I had a question regarding SGX and Gramine. Yes. So as I know, the enclaves have some memory limit, but with Gramine, you...
Yeah.
Yes, okay.
So on current generation mainstream servers, there is a limit that all enclaves on, let's say, a third, fourth, or fifth generation Xeon CPU, Xeon Scalable, I should say, are either in total a maximum of 64 gigabytes or 256 gigabytes or a terabyte in a two-socket system. So those are the different different SKUs that you can buy from Intel, basically, that make up that space. That's depending on the main the memory space that you have in an infrastructure, the memory capacity. You take a portion that you can configure and reserve it away for secured memory, for SGX, and that'll be the maximum that you can host on that particular system. And yeah, these memory limits are, as I said, in total maximum, depending on the SKU in the stack, 64, 256, or 1 terabyte in a 2-socket system.
So this limit is for, I mean, one enclave can take, I mean, 100 gigs.
It can. Yes.
Okay. So because I was under the impression that they had some limit, like 100 megabytes and stuff like that.
No,
so this is an older generation.
This is an older generation. This was on our entry-level servers who had, and on our now deprecated client version of SGX, where enclaves had this limited size. Yes.
Okay, so then this makes it okay. Gramine can put an entire application inside the enclave.
Yes.
Okay.
There is actually code demonstrations from known projects, known open source projects that all fit well within SGX enclaves, and that includes databases, key value stores, etc. So you can put a lot inside an enclave.
Okay. Thank you very much.
Sure.
Thank you. And we have another question. I don't know if you are able to see the Q&A window, or I can also read it loud.
Please go ahead.
Yeah, it's from Philip Neuschwander. So what is the added value to have the connector in a CC environment? The provider connector will push the data directly to a consumer's data sink, Azurite, without handing over the data to the consumer side connector. Wouldn't it be way more important to protect Azurite and the applications that access Azurite than to put the consumer side's connector inside the CC environment?
Good question. And this is, as with all things security, it depends on your attack vector. And the attack vector that we are protecting against here is if someone wants to basically attack the business logic of the connector in setting up these data plane connections. So basically controlling, keeping the control plane completely undisturbed. You may argue this is not important to you. That's fine. If it's important to you, for example, if a connector is sitting outside in the field and you don't have control very well over who has access to the system, physical access to the system, that is where potentially you would be able, with Gramine, with attestation properly included, I should say that, definitely with SGX, to, for example, avoid a man-in-the-middle attack, that someone doesn't, in whatever way, insert a rogue connector in the way, for example. So that's, yeah, as I said, it depends on your attack vector. We demonstrated this one.
Awesome. So I don't see any raised. Oh, there is another one. Okay, I think it's in the chats.
Yes, thank you. So Markus, you mentioned that you started with SGX because this was the technology available when the project began. So how would you see the things now? Because if I look at that slide with the trust boundaries, so when should we go with SGX and when TDX is more suitable?
I think this is probably down to the strictness of your security requirements. SGX is typically being used and favored whenever the data to be protected is highly critical. As you saw, we also chose it for healthcare data in this case, or healthcare use cases, I should say. It's not the data itself that's being protected in there. But for healthcare use cases, but that elevates the criticality. Also, I said SGX is better controllable because of its small attack surface that it has. In addition, and I don't want to talk about this for too long, there are aspects of attestation that are much more strict with a simple single process environment than they are with a larger virtual machine based environment, which has internally a lot of dynamicism, and so makes it hard to create a, let's say, a single consistent hash that could work as the proof of this is my trust execution environment, and I can really trust it. So that's mostly the case. In terms of what we would choose nowadays, I think promises that exist are container/Kubernetes environments that are being constructed these days that make use of virtual machine encryption, like TDX. So things like confidential containers is a promising project of the CNCF in this case. There are other open source projects like Edgeless Systems Constellation that do similar things. So you can use virtual machine-based confidential computing with similar effects and just deploy containers on them. And I would probably pick and choose something like that if I started these days. If I want to have a simple path forward, if I want to have strong security assurance, I'd still pick SGX.
Okay, thank you.
Sure.
Thank you very much. So we are already over time, but we have another raised hand from Idris Youssef. I don't know, Markus, if you are able to.
I have. Let me see. I think I have more time. Stay on. Yeah. Let's keep going.
Thank you. Much appreciated.
Thank you for accepting the question. Thank you for the presentation. I have a small technical question about the monitoring of the EDC. Were you able to deploy some tools that helps you monitor the EDC in terms of resource consumption and monitoring also the coming request from different other connectors? I mean, if you were able to, for example, identify which connectors called which one and what was the request exactly and what's the result of the request? Thank you.
I think this is probably a question that Sergiu can answer better than I can.
Well, our focus was to get the connector running on SGX, and ultimately there's no difference in how the connector runs on SGX versus non-SGX mode. It's only the security part. So monitoring the incoming, outgoing requests, we assumed is the same, and well, that wasn't our focus. Just to quickly answer to your question. But maybe that's something, maybe that's a question for the Eclipse Dataspace Connector and the minimal viable demonstrator maintainers, perhaps.
Perfect. So thank you very much all, and I think we can conclude the webinar today. So thank you very much, Markus. Thank you very much, Sergiu, for your contributions here. That was really very comprehensive and straightforward, and that's really much needed in this tech talks, frankly saying. And thank you everyone who attended this call. So looking forward to further collaborations, and I think you can always feel free to reach out to our speakers today and also contribute to the work.
Perfect. Thank you very much.
Thank you.
Anil.
Thank you.
Thank you very much. Have a great day.
Cheers.
Bye-bye.
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 Goodbye.